Okay, any questions so far? We will answer question first. Any question? No question? Any question on the homework, everything? Okay. First is I look at the score for the what? For the quiz 3A. I'm not sure, but every year when I teach for 3 years so far, the quiz 3A I think is the lowest one. I mean, a lot of people got red, orange. Okay, other tests actually are better, but quiz 3A usually is lower. So what can we do? I probably will give a third try. Is that okay? Is that okay? So let me edit it. Hello, any question here? So this one I'm going to allow third attempt because really too low this time. But it doesn't happen only this year. It actually happened every year. So I'm going to allow for third attempt. Why is that? Because this 3A displacement vector is pretty important. If you don't get it, you're not going to make the rest of the course. And I don't know why, but because I have been teaching this course many times, every year this 3A always is the lowest point. Actually, later quizzes, the score can be higher, but I don't know why this 3A always end up to be the lower one. Okay, so I'm going to give the 3A another try to everyone. At least a 3B actually is a little bit better, okay? Not so many red. But 3A, I don't know why there are so many red. So please study the 3A. 3A is displacement vector, so it actually can be different from the rotation, and we focus more on rotation. So please spend more time to study the displacement vector. Okay. Any question? Hello. Any question so far?
I don't think so.
Okay, no question is okay. So I'm going to send a message, okay? I send a message to everyone. Okay. So 3A we allow third attempt. And the first thing I would like to say, second, right now, I just would like to share some information. The Bay Area, a lot of layoff, Google, Twitter, Amazon, and Meta. Okay, almost every company are laying off people. So you must be good to stay in the company. Okay, so must train yourself good at the coding, at your basic skills. Okay, so if there's no question, we are going to just briefly talk about Jacobian. Okay, again, this video and the course video we already pre-recorded. So for the complete version, please look at the website. Okay, website's material, teaching material every week. The purpose for us to have this discussion is focus on answering your question or homework and assignments. And other than that, I will go over the key points for each lecture. Okay, so today's lecture is inverse kinematic. I'm sorry, it's actually. I'm sorry. Yeah, I'm sorry. Let me check. Okay, it actually. Oh, we haven't talked about Jacobian, but we will talk about Jacobian first, and then inverse Jacobian. Okay, and then inverse Jacobian. So today we are going to focus on differential kinematic using Jacobian and inverse Jacobian. Okay, and this dark blue version is the graduate school one, so it's actually harder. We are supposed to teach this level, but some of you are just learning robotics for the first time. So we use this simpler undergraduate version first. Okay. Okay, so we talk about the Jacobian metric today. First thing is that what is Jacobian, and then velocity analysis for robot. Okay, so we do have 6 dimension, 6 degree of freedom. Okay, we talked about this already. Okay, SYG and 3 theta. Okay, 3 rotational theta. So what is the kinematic relationship? Actually, we do have joint space, joint variable. Here, the joint variable we list down 6, but well, because we want to talk about 6 possible directions. Okay, 6 possible directions, but here it doesn't mean that always be theta. So it can be theta, can be d. Okay, some joint variable can be d. So it really depends on your type of the joint. Can be prismatic, can be revolute joint. It depends. Okay, so here, number 1, it may not be 6. Okay, maybe 5, maybe 7. Okay, we don't know. The number of joint, we don't know. Okay, that's called joint space. So joint space is where your variable is. Where your available space is. And we also call it what? Configuration, right? How you configure your robot. Using this different joint variable, you can create your configuration. And then this one you do using the forward kinematic. FK means forward kinematic. You use a forward kinematic of your theta, you will get your what? Your desired location XYZ, right? You get that. So this one, given theta, you get XYZ. So these are the so-called what homogeneous transform metric, Derivative Hardenberg transform metric. So this actually is the equation for that. Okay, so you get from your control variable, you get your XYZ. Okay, you get your new XYZ. And here you do have your XYZ, and you also get your theta phi per c. Okay, you also get your theta phi per c. Theta phi per c are the 3 angles. What 3 angles is the so-called roll, pitch, and yaw angles. Okay, it's a roll direction. Roll is green one. It rotate along here. Okay, along the. So this one forward. So this is x. Okay, and then left right. So this one is y. Okay, and z. So along 3 way you do have rope. So that is the 3 theta, 3 angle you have on the different axes. So phi theta per c. This one per c, right? Actually, it actually is the different angles. XYZ is your locations. Okay, your physical location. So SYG is your n factors location here. Okay, where it move. Okay, it's your SYG, your position. Okay, so this one actually is in such a relationship. For kinematic, you get from the joint space to the touch space. Okay, and then from your touch space to go back to calculate for the joint variable, that's called inverse kinematic. So IK means the inverse kinematic. And we get inverse kinematic because we want to control our robot to the desired location of XYZ. We know that where we are going, and then we need to set the joint variable in a certain way for it. Okay, so far this is the forward kinematic, backward kinematic, but in the first order space. Okay, in the regular space. Now, if we take the derivative, it becomes the relationship between the velocity. Okay, so it's between the joint velocity and the joint variable velocity and the Cartesian velocity. Okay, so you do have the joint variables change on the left side. Right side will be your touch space change of the speed. So X dot means x direction speed. Y dot means y direction speed. Omega x means the rotational velocity along the x-axis. Okay, omega y means that the rotational velocity along the axis y. Okay, so that's different. These are different variables. Okay, in the when you take derivative. Okay, so this one, the Jacobian metric means that when you take the derivative on your forward kinematic, that's called Jacobian. Inverse Jacobian is the when you take derivative on the inverse function in inverse kinematic. Okay, anyway, this is the relationship. Okay, now let's look at how to derive the Jacobian Jacobian metric. Okay, so suppose the position and orientation vector of a manipulator is a function of 6 joint variables. So right here we are assuming that joint variable Q, joint variable Q1, Q2. So Q can be a theta 1, theta 2. Okay, I'm sorry, theta X, theta Y. Okay, or you on the joint variable. I'm sorry, actually it should be theta 1, theta 2, theta 3. Okay. Or can be a D1, D2, D3, actually displacement on each joint. Okay, so here we use a 6 because we use a 6 possible joint variables. So here, this number of variable can be, say, can be 5, can be 7, can be 2. Okay, it depends, it really depends. So here, based on this 6 joint variable, you will derive the what? Your desired position and orientation vector, okay, is to be xyz 5 theta per c. You will get this one. So your input is q, joint variable q vector, and output is xyz 5 theta per c. Okay, so that it's your system of equations. Okay, so that's assume that is a system of equation is H, and you put your Q1, Q2, Q6. That's assume that's a Q vector, joint variable Q vector Q, and then this one you have 6 functions. So x will be equals H1, the first function of the Q1 to Q6. Okay, Y will be another function. Okay, so totally you have 6 function because you do have 6 variable. So this one does actually take derivative. So your x, okay, here we do x 6 times 1 means that it's a single one column. Okay, x, big X means the SYG 5 theta per c. Okay, equals h of qn. N is the number of joint. Okay, qn times 1 vector. So you take the derivative of this one, this one d, this one dt. Okay, so this one dt, you do this one is what chain rules. So you do dhq, dq, and dq dt. dq dt is the q's derivative. So you've got this h function take q. So the h function dq, you will get a matrix because you do have some partial. You can formulate this one into a matrix using partial derivative. Okay, here this one is a function. So q derivative actually is a vector of n times 1. There is a matrix of 6 times n you can get. Okay, so that actually is this one. So Jacobian metric is this DHDQ thing. Okay, and DHDQ thing is actually a 6 by n metric. It is a 6 by n metric. So each one of them is partial H1, partial Q1, partial H1, partial Q2, partial HI, partial QN 6. Okay, you do from this one. This is called Jacobian metric. Any questions so far? Hello, any questions about? So basically, first thing is that you need to list down your forward kinematic function, and then x equals some q1 to q6. So using the x1, using the joint variable to formulate your x, using the joint variable to formulate your y function, then you take derivative, and you get this partial derivative metric. That's called Jacobian metric. Okay, that's called Jacobian metric. And then this Jacobian metric will have two things, two parts. One is the upper portion, is top three, we call it the linear velocity. Lower three, we call it the angular velocity. Okay, these are totally independent. Okay, you do not have to be this done this way. You put the omega on top, put the v on at the bottom. That's also okay. It really depends on how you formulate your formula. Okay, so this one is like that. So your Jacobian equation is your time space speed will be equal to your joint variable speed times the Jacobian metric. Okay. So if you know about Jacobian metric, given any joint variable speed, you will get your change on your XYZ. Okay. So that's let's look at one example. So right here we do have the XY location. We can formulate it using the link length L1, L2, and the theta 1, theta 2. The theta 1 is the joint variable 1's theta. Theta 2 is the joint variable 2's theta. Okay, and you formulate in this way. So let's see here your x location, including this portion and this portion. So this portion really is the L1 times cosine theta 1. Okay, this portion is L2 times theta 1 plus theta 2. Okay, theta 1 plus theta 2. So by this way, you can get your h theta 1, theta 2, h2 theta 1, theta 2. Okay, and your this one should be x. Okay, the position speed s dot y dot equal to Jacobian metric of the theta 1 speed and theta 2 speed. You take partial derivative of this one versus theta 1 and versus theta 2, you get such an equation. So this one is your Jacobian metric by calculation. Okay. Any questions so far? Any questions so far? So this one actually is how we derive the Jacobian metric. Okay. Any questions so far? Okay. No response. Okay. I'm assuming okay. So let's actually continue. Next one is a singularity. Singularity means that if the inverse of Jacobian metric cannot be calculated, such as the determinant of the Jacobian metric equals 0. Okay. So this one actually, when will this happen? A metric equals 0. When will this one happen? Say you have a metric, and the metric's determinant will be 0. Anyone know? In this case, you cannot find the inverse. Okay, then because this one will be 0 because if you have two planes, they are parallel. They are parallel, so their system equation will never have any intersect. Okay, will never have intersect. So when they are parallel, the determinant will be 0. Another case is that if the two planes they are overlapping each other, they are connected everyone, that will also give you determinant to be 0. Okay, two plane, they are overlap or parallel. So in this case, we call it singular. Okay, singular when the determinant of the Jacobian is 0. Okay, so that happened when what? That happened when your theta 2 equals 0. When your theta 2 equals 0, this one will be a singular matrix. So let's just think about what when theta 2 equals 0, what happened? Theta 2 equals 0 means that theta 2 is not moving. So what? You lose 1 degree of freedom. It becomes a baseball bat swing. You just swinging on a circle. Okay, that is a singular point. That is a singular point. Okay, that is a singular point. So when you have the when your determinant becomes 0, that means that your robot can never change. Your configuration is fixed. It's a singular configuration, and your theta 2 is always 0. Then you will get your determinant to be 0. Determinant of the Jacobian matrix will be 0. That means your theta 2 is 0. You are not moving the theta 2. Your theta 2 is fixed. Actually, it's 0. It never changes. So this the whole robot become a baseball bat, just swinging using the theta 1. Okay, and then you are fixed on a circle. You are fixed. SY is actually fixed on the circle. So in that case, this theta 2 is 0, 0, 0, 0. Okay. So it will be simple rotation. Okay. Okay. Okay, Jacobian metric. If A is an n by n metric and A plus is a pseudo inverse of A, okay. If A is a full rank, A plus it can be calculated. So because your A is not symmetric metric, so we try to create a pseudo inverse for A. Okay, pseudo inverse can be calculated based on these. In case that you do not have inverse, we try to come out with a pseudo inverse metric to calculate the inverse. Okay, this one is to check whether there is a singularity or not. Okay, so this one you can look at it. Okay, the operations. So Jacobian metric, we do have this one times x equal this one. Okay, and then we can calculate the pseudo inverse metric. Okay, this is pseudo inverse metric. A plus is like this. Okay, and then we can use that to calculate. Okay, whatever. So inverse Jacobian. Let's look at the inverse Jacobian. So here you do have the Jacobian equal this one. So if this side you actually multiply the inverse Jacobian, you multiply inverse Jacobian. Okay, so you see the will be equals inverse Jacobian times the velocity of the joint variables, right? So this one is here. Okay, so inverse Jacobian will be the inverse Jacobian times Jacobian times theta. Okay, so this one need to be one identity metric. Okay, this one need to be identity metric. So basically, your inverse Jacobian should be equal to your Jacobian divided by identity metric. Okay, that's not too hard to find the inverse Jacobian metric. You will be able to do inverse, find out the inverse Jacobian. Okay, so here that's why you need to have a pseudo Jacobian metric. Okay, that's why you want to calculate a pseudo in case that it's not symmetric metric. Okay, you try to calculate that. Okay, so inverse kinematic. This one is using your joint variable to calculate your this one to calculate your Cartesian variable. Okay, and this one is forward Jacobian, and your inverse Jacobian is the Jacobian metric divided by. I'm sorry, it's actually is a identity metric divided by your Jacobian metric. Okay, because your inverse Jacobian times the Jacobian should be identity metric. Okay. Okay, whatever. The one we talk about is actually previous things that we talk about. That when you see that determinant equals 0, this is creating a singularity. This kind of singularity we also call it boundary singularity. So boundary singularity happens when you lose your degree of freedom. You lose your degree of freedom. Okay, interior singularity means that there's a certain location that you cannot go there. You cannot go there. So that's interior singularity. Okay, so here we do have discussion about singularity points. Okay, and then next one is Jacobian metric operation. So, okay, so we do know how we can derive Jacobian metric. Okay, we do know how we can derive the Jacobian metric if we use math. So next one is, okay, use math. So next one is, so we do know about the math. Now the next one is that can we come up with algorithm? Yes, here is the algorithm to help you calculate the so-called Jacobian metric in a faster way. Okay, so the next one is computational. This is no longer mathematical derivation. Okay, so this is computational. So first thing is that you do have A vector, B vector. We need to know about the so-called A cross product with B. This A cross product with B, actually here you do see a IJK. Okay, this IJK is what is your directional vector, unit vector. So IJK means that your unit vector in the I direction, J direction, and K direction. So it's a SYZ is a unit vector. That's what we try to say. So here, when you try to see, you do have A cross product is B. Okay, you will get this one. Okay, AXAYAG. Okay, BXBYBG, and you do have IJK here. Okay, so let's assume that your X is. Let's use a very simple case that your A vector is equal to 1, 0, 0. So you do have this point here. Okay, on the x-axis 1, 0, 0. That's your vector here. Okay, B vector B 0, 1, 0. Okay, so B vector is right here. Okay, by doing this one, you use the right hand rule. You will see that your C vector. That's so this is C vector. C vector's value and direction will be this one. Okay, so how do you calculate it? It actually is this one forward. So AY plus BG. Okay, AY times BG is this one, and you want to look at this is X direction. Second one is your AG times AS times B1. Okay, so here you actually you do minus this one. I'm sorry. This is plus 1. Okay, so you have this one, and then you have this one. Let me see. This 1, 2, at least this you get I. Okay, so this AG BY. This is a negative. Okay, let me try one more time. So positive is from here to here, you time this one. Negative, you time this one to here. Okay, you get this actually this component. Okay, so positive one is AY times BG times I direction, right? This one you time this way. Negative one is actually you do use this direction here. So AG BY, but there's a negative. Okay, this both of these you will have this one I vector here. Okay, and this is the determinant of this one. Okay, determinant of this submetric. So it really is the determinant of this yellow one. Okay, yellow one. Okay, second one you do want to calculate J. So J is your positive going this way. It's actually is AGBX. Negative is actually you do have negative one is here BGAX. Okay, so it is really the determinant, partial determinant of these four elements. Okay, and putting the minus before it. Okay, third one is your K. Your K really is had a partial determinant of this one, and is actually including a K over K positive of this one times this one, negative of this one times this one. Okay, so this is the cross product. So let's put the value into there. Put the value into there. You do have 1 0 0 0 1 0. So AYBG is 0. AGBY is actually 0. Your ASBG is 0. AGBX is also 0. Okay, your ASBY is 1. Your AYBS is 0. So this one you get the whole sheet become 0 0 1. So your this direction A vector direction times Y vector direction, your cross product direction is right here in C vector direction. It's actually cross product using the right hand rule. Is that okay so far? Okay, this is the operation for cross product. Okay, any question? So to solve the Jacobian, we need to know about the cross product. Okay, so basically you do have a transform metric, a Denneby-Hartenberg transform metric of the T. C theta 1 means cosine theta 1, okay? And then S theta 1 is called sine theta 1. Okay, so you do have the such a matrix. And this one A matrix including the displacement, rotation, and orientation. So your T0I would be this, a series of the Denneby-Hartenberg transform matrix time together. Okay, we know that. Okay, so next one is your Jacobian metric of n degree of freedom is J1 to Jn. Okay, each J is actually a column. Each J is a column, and your row is actually fixed as a 6. So it's a 6 by n metric. Okay, it's a 6 by n metric that we know. So there, when there is a join. If it's a river join, okay. When there's a river join, then we're using the function of GI cross product with ON minus ON minus OI minus 1. So the cross product of these and these, and then GI minus 1. Okay. And what is G? What is O metric? We'll talk about it later, but key point is that you do have a vector of gi, you do have a vector of oi, and then you do gi times on minus oi minus 1, and here you do gi minus 1. This will be the Jacobian column I. If the I is actually a regular joint. If I is actually a prismatic joint, then the Jacobian column, one column, we call Jacobian column. That Jacobian column would be gi minus 1 versus 0. 0 can be 3 degrees, should be 0, 0, 0. So this is the gi and oi since actually is what? It's not just one variable, it's actually 3 by 1. It is what? It is the so-called omega and v. It's the so-called omega and v. It actually group of 3 variable. Okay, group of 3 variable. Okay, so that actually is the notation for it. Okay, that is the notation for it. So here gi is the first 3 element of the third column of the T list. Okay, these are definition. Okay, these are definition. Later we'll show you how to operate. Just remember gi are these one. You do not need to at this moment, don't try to understand it. Try to just knowing that you do have taking some component from some metric. Okay. Okay, let's actually look at this. This is a simple Jacob. This 2-dimension robot. One more time. Okay. So n equals 2. We are trying to find a Jacobian metric for it. So last time we do calculate the mathematical solution for it. Right? Last time we do use the math to solve it. Now this time we don't use math. This time we use the formula to find it. So this formula we do come up with Denby-Hartenberg map table that is. We do come up with 2 transform matrix like this. Okay, so you do have A1, A2. This is when you actually set up the Denby-Hartenberg matrix. You do come out with several of these. You do come up with several of these. You are supposed to time them together, right? So here, these are the A and these, okay? Now, you need to remember that we do want to use this A1, A2 to generate your G0, G1, and O1 and O2. Okay, so let's look at G vector. So G vector is what? G vector is the first 3 element in the third column of the Ti matrix. So G vector is the 3 element of the third column. So G vector really is this one. D vector is really this one. So let's give you this. Okay, no matter what it is, it's a third column. First three, remember that it's called the first 3 column, first 3 element in the third column of the Ti matrix. Ti matrix, okay, your Ti matrix, you actually, oh, I'm sorry, should be using this one, So actually you get this one, but it's the same, Okay, so this one, T01 is actually this one, so your G0 is actually get this one. G1, you get this one, okay, but still in 001, okay. So that is your G0, G1, G2 being determined in our. Next one, you would like to look at the O vector. O vector is the first 3 column of the 4th column. First 3 element of the 4th column, so it actually is, this one is your O. This one is your O vector. So we do have O0, O1, O2. So O1 is this one. O0 we assign with 0, 0, 0. O2 we assign with this one. So by this way, you generate your G and O using. So let's review it again. you come out with your Denby-Hardenberg metric. Is over here. Using that, you derive your AI. Okay, AI actually is this metric for each stage, and use the AI, you calculate the T01, T02. Okay, you come. This one really is A1. This one is A1 times A2. Okay, you get this one. So from the metric you got, you extract your Z vector and your O vectors. And then once you get these two kind of vector, you kind of plug in to calculate your Jacobian column based on those metrics, vectors, based on those vectors. Okay, so this one actually, let's look at n equal 2. Your Jacobian 1 is like this, your Jacobian 2 is like this. Now, you need to find your Z0, O2, okay, whatever sits. And this fusing, you will get your Jacobian vector of this after calculation. There's a cross product you need to. This one actually is what? This one actually is your metric cross product. This is cross product. Okay, cross product of two vectors. Okay, cross product of two vectors. You get this. This is your Jacobian column 1. Okay. Your Jacobian column 1 is like that. Your Jacobian column 2 is another one. You calculate this. And eventually you get your Jacobian column 1 and Jacobian column 2 is like this. And then you actually will be able to find out your Jacobian metric. So from your Denby-Hardenberg per stage vector, you calculate your total transitional vector metric. And from there, you extract your O0, O0, G0, O1, Z1, O2, Z02. You got the Jacobian columns. You got your JR is a rotational joint. JP is the prismatic joint. And you select whether it should be rotational or prismatic, and you get your J1, J2. It's okay so far? So Jacobian metric is not a mess. It actually is an algorithm, how to help you to, okay, behind the screen, we do need to have a mesh for Denby-Hardenberg things working, okay? And Jacobian metric is an algorithm. Okay, what I should say is that, okay, Jacobian metric is a mass take derivative, but there is an algorithm that you can calculate it, and that is summarized in this chart. Any question? Hello, any question? And then you get your Jacobian. And once you get your Jacobian, you try to come out with your inverse using the, if it's symmetric, you can find the inverse, right? If it's not a symmetric, you use your pseudo inversion to get your inverse Jacobian. Okay. Is that okay so far? I'm trying to show you the way to do it, okay? So this one, your Jacobian, let's look at the gradual levels of material, okay? This one, you do have Jacobian metric. You do have your John variable speed will be used to calculate your positional vector available speed. Okay. So your I equals A times A inverse. Okay, A is any metric. So this is used to calculate the Jacobian inverse of Jacobian. Okay, so this is like that. Okay. And then your inverse Jacobian times the positional vector, you get your required John variable speed. Okay. Okay, and then you can look at this one. Okay, to solve your simplify. This one is the similar to the previous chart. Okay, the two bar one, theta one, theta two one. It said that the G, we do not look at G, we only look at X and Y. Okay, and you come up with the trying to calculate your Hardenberg metric. Okay, and you come up with your homogeneous metric H0, H1. Okay, so you calculate that. That's the portion you come out with H vectors, and from the H vector metric, you extract your G vector omega vectors. G is SYG velocity. I'm sorry, SYG variable. Omega is theta, 3 angles. Okay. Omega is an O that you see in the previous note. Okay, and you do try to look at it's a prismatic joint. You do have linear vector and revolutionary vectors calculation way. Okay, and these are the formula. And okay, so this one is how you calculate your Jacobian. Okay, so Jacobian is a algorithm, and then from that, after you get a Jacobian, you do Jacobian metric, and then what? Calculate the inverse for it. Okay, calculate the inverse for it. You get the inverse of the Jacobian. Okay. Okay, there's a standard way to find your inverse Jacobian. Okay, there's a standard way to find it. So you just follow your way to do it. Okay. Okay, so that's that. And then there's several approach to find a closed loop solution. So here we do have this one is using your mathematical and algorithm to solve it, but there are also possible that you use algorithmic solution. So let's assume that you do have a error vector. Okay, so you do not know about you actually would like to find a approximate solution. Okay, so you actually do many iterations. So you do, and at the end, if your Q function converge, your error will be 0. Your error is the difference between your estimate value and your real value. Okay, so that's assume that when the error approaching 0, your value should be actually equivalent to your numerical solution. Okay, so this one is using numerical solution to find. Okay, so and you can also use the pseudo inverse to find. Okay, so this one is you can derive a mathematical system to look at the inverse Jacobian. Okay, let's look at this one. So here this Q is your joint variable vector. So you use this Q to control what? Control your robot. And your Q will have feedback and use a certain metric, and you have to estimate the E. And estimate the E, and your desired value will have some value, some error. This error, when it approaches to 0, then your Jacobian speed is your desired Jacobian speed. So this one is actually a control loop, electronic control loop to control your variable Q. So it really is a hardware implementation of this error dynamic. Okay, it's actually a hardware implementation and it can be used to implement the so-called inverse Jacobian calculation. So to the end. This one is the real configuration that we use for your control system. Okay, and there are some Jacobian transpose, some mass, and you can calculate and arrange it. Okay, with different way. So there are different different robot arm. You can work on it, and you can actually try to use the numerical system to solve it. So here we have more mass to talk about how this system will work. Okay, so this we call it a closed loop solution. Okay, so closed loop solution is that instead of using the mathematical calculation, we can also use a approximation system doing many iterations and using the closed loop system and to solve it. Okay, and then you may also use a second order inverse schematic algorithm. If we further take another level of the derivative, so you get second level. Second level, you would get x acceleration, right? And when we get x acceleration, we will know how much force need to be used. Okay, because velocity is momentum, it's not force. You need to go to the acceleration, then that's the second order acceleration. That is your force. How much force you need to use, right? And that you come out with second order inverse kinematic system diagram that is using your joint variable that you want to have, and you actually do estimation filter to design it. Okay, using the feedback system to design it. Okay, so that is how you control the acceleration. Okay, so you can use the open loop Jacobian algorithm. That's the one we derived in the beginning. Okay, and then you can use closed loop Jacobian that actually is numerical, and usually when we implement hardware, we are using the closed loop inverse Jacobian. Okay, and then you can look at the control variables, how it converges or not converge. Okay, you can look at that. Okay, any question so far? I try my best to talk about the key idea. Okay, the key idea for this different one, and other stuff you have more joint, the system will be more complicated. Okay, so basically this is going to lead to the trajectory planning. You have your desired joint variable. Okay, we want to know how to control it, but you do have your passive specification. So say we want to move the robot from point 1 to point 2, and then we need to find out how much force we need to use for the motor, right? And how much speed we need to control. So that actually trajectory planning. Given your estimated destination and your plan the destination, you can come up with a path planning. Okay, so input is your Cartesian space path constraint. Okay, output is a joint position, velocity, reference value to control the controller. So that's the purpose of doing the inverse Jacobian. That is, given you a path, giving you a certain path xy, desired x, okay, and speed. What kind of joint variable you need to have in order to control your robot to go to the right direction or pick up the right shape. Any questions so far? Any questions so far? Hello, any question?
No, Professor, we got.
Okay, how about homework or assignment questions?
Yeah, I was actually wondering if you could kind of go over assignment 4 and
Assignment 4, okay.
yeah, assignment 4.
Assignment 4, as far as I can remember, is on the workspace, right? So you need to plot some workspace data. So let's look at this one. This one is spherical manipulator, okay. So we do have this one, we do have a theta 1, theta 2, and there's a A3. A3 is a link. So your n effector is supposed to be here, right? So let's don't think about theta 1. Let's just think about you actually moving this one here. What do you get? A circle, right? Don't think about theta 1. Just think about if your theta 2 rotate, you get a circle, right? Right?
Right, yes.
So this circle you will move around for 330 degrees. What do you get? What is your workspace? You have a circle, you move around for the whole 360 degrees. What do you get? You do have a circle here, and you kind of creating it, moving around it for 360 degrees. What do you get? What do you get? You get some sort of donut, right? But this donut is not solid. It's not solid inside. It actually is only a pipe of donut surface. Does that make sense? Hello?
Yeah, I think it does.
Yeah, okay. So if that is what we want to have, then the first problem is that use a mathematical model to determine. So you tell me which workspace it is. So that means that you have to describe this a donut using the 5 variable we have: A1, A2, A3, theta 1, theta 2. Is that okay?
Yes, I think so.
Okay, so that's actually this one. And then if possible, can you draw a diagram using Python to show it? Right? Is that okay? If possible, draw some chart, some program that can show it, okay? So what I can tell you is that some people do create let me see. Well, I don't have previous year's solution, but the end result would be a donut, and then I try. Okay, let me try. So the end result, I'm expecting a donut, and you need to use your Python to draw it. Is okay? Let me see. Do I have it? I should have the code. Okay. Homework solution. I cannot tell you how to do it, but actually this is what we get. Does that make sense?
Yes, it does.
Okay, then how to come up with this one? You need to use mesh. Mesh is a matter drawing. There's a function called mesh. Okay, look at it. Try it. Okay, so basically, if you cut a donut, it actually every single one of it is a circle. Okay, every section is a circle. Okay, and A1, A2, A3, you can assign your own value. So not a uniform solution. Okay, maybe somebody's donut may be bigger. Okay, it's okay as long as you draw the donut shape. I'm happy. Make sense?
Yes, it does. Thank you.
Okay. Any other question?
Actually, I do have like one more question on assignment 3, if that's okay.
Yeah.
I was working on trying to get the extender, and I was a little stuck on that. So I know last time when we were talking about it, you showed me the matrix that had like the extender like kind of inside of it. Was that like the matrix for like the rotational matrix from joint 2 to 3? Or I guess I'm not too sure where to try to implement the extender.
Actually, extender is easier than revolute joint. Okay, but somehow because we talk about more rotation, so I don't know why. That's why I still wonder. It doesn't just happen this year, but every year that Q3A is always the lower one. I don't know why. Okay. So here you do have a extender, okay, extender, you do have extending with D. So D is a joint variable. So when you set up your SYD up to here, right? So your end effector, so this point actually is based on a friend tree, right? Let's assume that your friend tree is this way. Let's actually take out this one. Your friend tree is this direction. So this is your G direction. This is your S direction. Let me see. Let me check. Okay. This is your Y direction. Okay. So your end result is that right now this end effector location is actually at the 0, 0, D location. Is okay? This one end effector is only a variable, but this one because your end effector is on the last stage. If there is an end effector, if there is a extender, after the extender is another revolute joint, okay, it will be more complicated because here you have a friend, here you have another friend, then your extended this variable is no longer a coordinate of the end effector. It will be part of your transform matrix 0, 0, D, 1 here, and the last column. Is okay?
Yes, it is. So in our
In our
have
last one, you just actually do what? You just do look at the D. Okay. So last one you do have extended. Extenders metric is 0, 0. I'm sorry. Extenders what? Okay, you still need to take care of the rotational part. I'm sorry, orientation part. But the extender metric would be 1, 0, 0, 1. This one. Okay, so you do have S, Y, G, 1, right? So the rotational part is actually identity matrix, so no change. Extension of 0, 0, D, you extend and you will get there. Is okay?
yes, it is.
So right now, because your G will be at the D location, your G actually is at the D location, right? So because this one is your D location. So this one here, this one you actually you can basically put a, let me see, this one you do the last one, actually row 1, colon 1, row 2, colon 2. row 3. This one 0 is okay. You get a D. Is okay? You put a 0 over here, it's okay. It's not on the extender, the last stage you based on the extender, you can put that over there. Put a D on the destination metric. So here, this one you put a 0 is okay. But if you put a 1 over here, two-way, either way it works, okay? You put a 1 over here, and then this one you can fill in a D. Or you put a D in here, you put a 0 here. Is that okay?
I think I get it now.
I'm sorry. If you put a D here, you put a 0. You will time this one and use this one to get it. Is that okay? If you put a D there, you put that. That means that you consider that it's the last transformation. If the last one you actually don't consider it's not a transformation, it's just your coordinate on the surframe. You put a D over here. Is that okay? Either way will work. Okay. That means that your frame three, one way is that you put your frame three at the end effector. Okay, then this one is on the frame location is on the transform metric. If your frame three is put on the end effector. The other way is that you put your frame three on the extender, and your end effector is only a point. Either way is different. Okay, this way, the right hand side way is you do put your SY and your G is D. Okay, does that make sense? So here you do this one, it's good enough. Okay, this is system. If you do extender this way, it would be SY and Z. Okay, 1. And here is G 1 0 0 0 1. Okay.
Yes, I think I get it now.
Either way will work. Okay. Any other question?
I don't think so.
How about other one? Any question? Raju, any question?
Yeah, actually,
Yeah.
I have submitted my project proposal
Yes.
weekly, but I haven't received any feedback or any grade for that.
We haven't graded yet. I haven't graded yet. Yes.
Yeah, just I want to know like whether is the project is accepted or
We
I need
don't give the suggestion is actually accepted or not. We just actually, as I emphasize, this is an open project. As long as you do some project on robotic, it's okay.
Oh, okay. And
we don't give guideline, but if you do something totally not related, it's not okay. But here we just want you to do proposal. The whole idea is making the right proposal. So if your project is not accepted or not related to robot, we'll tell you that the topic is too far. But you can choose other project to work on. We do not say that no, you have to. There's no need to resubmit the proposal.
okay, yeah.
So it will be judged based on whether it's a good proposal or not. If the topic is irrelevant, we'll tell you, hey, please don't do work on this one. This is not robotic project. That's it. We don't give a personal judgment of this is a good project or bad project to work on. Is okay?
Thank you so much, Professor. Yeah.
So it be graded independent of the final result for the term project. It is a proposal writing project. Okay.
Okay, and I haven't received a grade for my week 3 project as well.
Yeah, we
Sorry,
haven't
not a project.
yeah, we haven't graded yet.
Okay.
Yeah, we haven't graded it. So this week, okay, it's a week 4 planning. I haven't graded. Okay, and programming assignment, some submit early, some submit late. So early one I already graded, late one I haven't graded. So if you submit earlier, I will grade it earlier. You know what I'm saying? I'm not sitting here 24 hours to do grading. I have other things to do, right?
Yeah.
So whoever submit late will be graded later when I find a time slot to work on it. Is that okay?
Okay. Yeah.
Any question about assignment 3?
Yeah, I'm good, Professor. Thank you.
Hello, Professor. I think
Yes.
how much we lose points for late submission?
How much what?
Points we lose for late submission.
Late submission, if you are within a week, usually I don't deduct, right? If we are more than a week, usually maybe 10 points or something. I don't give a significant deduction, but I still need to differentiate people who submit on time and late. You know what I'm saying? Otherwise, not fair.
Okay.
But we do not say 150, we do not deduct to 0 point. No, we don't do that, right?
Okay.
So maybe 5 point, maybe 10 point, depends on how far away you are late. So you see some students still missing on program assignment 1. Okay, some students still missing on program assignment 2. So when I do grading, you see, this is not an easy job. I need to go back to check if here there's something coming. Okay, right now it's still only week 3. When we go to week 8, okay, some of them still haven't submit week 1. So I still take them. As long as you submit, I still take them. It said that if you are more than 1 week late, I may take some deduction. But usually it's -5 or -10. Is that okay? Is that okay? And
Okay.
when will I cut off? I told you before in the discussion before that actually at the last day of the semester. So say our last day is December 17, right? So Sunday night 18, Sunday night 18, 11:59, Sunday night Central Time. Any submission after this time will get 0 point, okay? I told you it's a real deadline, deadline. After that, don't negotiate, okay? I don't actually give any point. Before that, any submission, even though you are on week 8, you submit week 3 for me, I'll still give you grade, okay? Is that okay? But if you pass this time, that's the last day, that's 9, you still cannot do it. Don't ask for extension. We are too late already, right? You did not finish within the semester because what? Everybody go vacation already, right? And I will be required to submit a grade on the 8 p.m. Central Time of the Tuesday. So I need Monday the whole day to do grading and do adjustment. Okay, I need the whole day to do adjustment. So some of you are not doing great in the usually programming assignment. I don't deduct that much point, but quiz you will see that it's actually will differentiate people who study and who don't know about it. Quiz will be setting people apart. So at the very end, I can say that I still have 200 points. I mark it as the participation point. I will use that to curve the whole class. Is that okay? But that depends on actually the whole class situation. I'll use the party. So usually how I do it, usually this one should be positive. Okay, number one, I can guarantee that I don't use the participation point to deduct people. Okay, so actually at this one, you can know that this one is positive. Second, when we do the overall grading, your base point is maybe 3,000. I don't remember that. So with the participant point, the total point may be over it. And we use the total point you have divided by the total base point. Base point not including this participant point too. So this kind of adding will boost up your point up a little bit. Okay. It's okay. And how much I'll give you, I don't know. I actually depends on how hard this class working now. Okay. The goal is controlling the number of A within 1/3 of the class over 2/3 of the class. So we don't allow A to be over 2/3, right? That's actually ridiculous. Almost the whole class got A. That's actually ridiculous, right? Some people even don't turn in homework. That is not fair. But if our A drop down to below 1/3, then I'll try to boost up. So the number of A is within this range. Is okay?
Okay, Professor.
Unless that everybody do so well and everybody score more than the A range, okay, then I have to, according to the student's grade, we cannot deduct student, right? So basically, usually I'll try to control within 1/3 and 2/3. Is that okay? A minus, I'll try to control it within this range.
Okay, Professor.
Is that okay?
Okay.
That's how this participation point work. But if you say your class is better, okay, you still every week there are some students showing up for the discussion. But some class I teach before the whole semester, 0 people show up, right? The whole semester, 0 people show up in the discussion and class. And those class, I do keep close to 1/3 or even below 1/3 for A, because the whole class is not started. There are one class before that happened that way, but it's a very rare case. Is okay? Any question? Okay, I will just say this course is not an easy course by the technical contents, okay? But we try to make it a little bit enjoyable, okay? This one is a graduate course and doing a lot of math and programming. So it is not an easy course, I know. But what we want you to do is that you do pick up the mathematical package. Okay, nowadays there are tons of everywhere. Okay, you do want to become a good and actually programmer and also knowing about math well. The robotic knowledge you know will benefit your data science. That benefit your many different fields. Okay, but right now the data is everywhere, so you got to be strong to survive in the job market. Okay. Any more question? Quiz 4, let me check. Okay, quiz 4, let me check. Quiz 3A, I already decided to give you one more try. Okay, let me see. Let me look at the quiz 4 quiz.
Yes, Professor. For quiz 4.
Quiz 4, 3, okay, there are a few red already. Okay, I'll see. Okay, if they are continue to have red, 2 tries still not good, I'm going to give one more try or 2 more try. Okay, usually one more try.
Okay.
Okay.
For quiz 4, sir.
But because the submission only 4 out of 14, so at this moment I don't know. You know what I'm saying? The number of submissions still below once, just about 1/3, right? We'll see. Okay. Any question? Okay, I'll consider that. Okay. You're confused. Okay, I know it's not easy. Okay.
Okay.
I'll consider that. Okay. If actually more than half people submit still have quite a few students, then I'm going to add one more attempt. Okay. But,
Okay, sir. Thank
but
you.
remind me if actually 1 week later they still there are some I haven't changed. Okay.
Okay.
Then I'll give you explanation whether everybody do well or actually just a few people, right? Just a
Okay.
few people, then I will not give another attempt. Is that okay?
Okay.
Okay. Any other question? Technical question? Any question that you bothered in you? Okay, remember these are different metric, even the Jacobian we talk about. Okay, even the Jacobian we talk about today, it's not only useful for the robot. Let's assume that you do have some sort of system equation. You take derivative. Everything like that would be useful. Okay. It doesn't have to be a robot metric. It can be any metric. The Jacobian can be used. Okay. So it's not only for robot. Robot is just one application for this. Okay. Okay. If no question, that's it for today. Okay. And keep doing work hard, and then let me know if there's something I can help. Okay. I'll consider the quick forward. I think one more attempt, okay, after 2 or 3 more, because you have 40 people, and if half of them submit, and say half of them cannot do it, okay, we will give one more attempt, okay? Okay,
Okay, sir.
if no question, that's it for today, okay? Thank you. See you next
Thank you
time.
so much, Professor.
Bye-bye. Bye-bye.